Well, let's see. I said the last lecture would be the last Calculus 1 lecture. I have a little bit more I need to talk about, namely integrals that involve natural logarithms. And here it is. Remember that the derivative of natural logarithm of x is x to the negative 1. Or equivalently, oh my goodness, shame on me. The derivative of natural log of x is equal to 1 over x. And so according to what we know about antiderivatives or integrals, that would mean that the integral or antiderivative of x to the negative 1 is natural logarithm of x plus c. And in terms of this result, this means that the antiderivative or integral of 1 over x is natural log of x plus c. It's going to be the function that we had to compute the derivative of to get 1 over x. So natural log of x plus c. And for some reasons that are rather complicated, we need to do a little bit better than that. And here's the issue. The issue is this. If we have 1 over x, and we want to compute the antiderivative of 1 over x, it's possible that x could be negative. But oops, if we stick a negative number in here, remember the entire Earth and our solar system is going to get sucked into that black hole. 1 over x, it is possible for x to be negative. Here's the graph of y equals 1 over x. And so, x can be negative. But if we take a negative value of x and plug it in here, bad things happen. And it turns out that this can be remedied very simply. Instead of having the natural logarithm of x, we just have the natural logarithm of the absolute value of x. This is what it turns out to be. So we didn't know what the antiderivative of x to the negative 1 was before. Remember, the power rule works for all exponents of x except n equal negative 1. Well, this gives us the antiderivative of x to the negative 1. It's the natural logarithm of absolute value of x plus c. And equivalently, the antiderivative of 1 over x is the natural logarithm of absolute value of x plus c. So, let's comment on this. Maybe we can do a quick integration exercise, okay? Just to get the ball rolling. Okay, let's give this thing a go. I look at this thing and I'm not really sure what to make of it. Except I do know that we have been training ourselves to look for function derivative pairs and approximate function derivative pairs. And this numerator may be approximately the derivative of the denominator. Let me rewrite it just so that I can be absolutely sure. If this is the derivative of the denominator, then this is going to be part of our dx. And we'd like for our dx to be in the back, in the rear of the integral, so to speak. So let's see. The derivative of the denominator is 6x squared plus 6x. Oh my goodness. This is a constant multiple of the derivative of the denominator, isn't it? This is 1/6 the derivative of the denominator. So the denominator and this function do form an approximate function derivative pair. I will be a son of a gun. Okay, step 1. Is U sub appropriate? And first thing we ask, is there a composite function? And you know, this is kind of tricky. There is a composite function here. The answer is yes. And the composite function is 1 over 2x cubed plus 3x squared. Now, why is this a composite function? Because we can rewrite it this way. See, this is a function raised to a power. And this is the outer. And this is the inner. So, yeah. And this is worth remembering. Anytime we have 1 over a function, that's a composite function. Now, we didn't really know that before, but we see it now. 1 over a function is a composite function. And our reasoning on that is we can rewrite it as the function raised to the -1 power. It's a function raised to a power, so it is a composite function. And our rule of thumb, that we let u equal what? Do you remember? The inner function. So that means that u equals 2x cubed plus 3x squared. And now we go on to look for maybe not an exact function derivative pair, but either an exact function derivative pair or an approximate function derivative pair. And we've already seen that we have that. The function is the denominator, 2x cubed plus 3x squared. And the derivative, x squared plus x. And our rule of thumb is to let u equal the function of the function derivative pair. So that means that u equals u equals 2x cubed plus 3x squared. Now we go to Criterion C. And you remember what that is? Do criteria A and B suggest the same choice of u? A says let u equal 2x cubed plus 3x squared. B says let u equal 2x cubed plus 3x squared. So yes, criteria A and B suggest the same choice of u. So that means U-substitution is a go. Step 2. Help me out here. What is it? Compute du. And we have u equals 2x cubed plus 3x squared. And that means that du dx is 6x squared plus 6x. And du is 6x squared plus 6x dx. Now, we didn't have an exact function derivative pair. We had an approximate function derivative pair. We were off by a constant factor. And because of that, I'm going to put an extra line down here. I'm going to leave it blank. Later on, I'm going to need this. Now, my third step, what is it? Step 3, analyze in terms of u and du. So let's see, we had written this as 1 over 2x cubed plus 3x squared, and the derivative was x squared plus x. So this is what we had. And remember, u is 2x cubed plus 3x squared. So this part is 1 over u. Now we try to analyze this part in terms of u or du. And do we see x squared plus x quantity times dx anywhere? We don't. But we see something like it. We see 6x squared plus 6x dx. And so we ask ourselves, what would we have to multiply both sides of this equation by to make the right-hand side look exactly like this? And the answer is we have to multiply by a sixth or divide by 6. So we multiply both sides by a sixth. So x squared plus x dx, that's 1/6 du. There's our integral in terms of u. Now, what do you think I'm going to do with this constant factor of 1/6 in the integrand? Move it out front. That's right. Take the constant factor and move it out in front of the integral sign. Now what? Step 4. Integrate. And of course, when we do U-substitution, we always integrate in terms of u. And just for the sake of comparison, suppose we have 1/6 the integral of 1 over x dx. I beg your pardon. Just to help us with this, consider the same expression in terms of x. We have a constant times an integral. So we write the constant down, and we have, whoops, and then we're going to compute the integral or the antiderivative of 1 over x dx. And that is natural log of x plus c with the x in the absolute value bars. Now the only difference between this and what we're actually integrating is the name of the variable. Up here the integral is in terms of u and du. Down here the integral is in terms of x and dx. Well, this integral is going to do to u what this integral does to x. So we're going to get 1/6 natural log of u plus c. There, so we integrated. And now we have one more step. Re-express in terms of the original variable. So we had integral of 1 over 2x cubed plus 3x squared times x squared plus x dx equals, in terms of u, it's 1/6 natural log absolute value of u plus c. But we want it in terms of x. So how do we convert from u to x? We go back to step 2, where we find our rate of exchange between u and x. 1u is equal to 2x cubed plus 3x squared. So this will be 1/6 natural log absolute value 2x cubed plus 3x squared plus c. And voila, we've done it. Before we do another example, let me make a few remarks. Some words in retrospect before we go on to another example. The antiderivative of 1 over u du is natural log of absolute value of u plus c. This is just the counterpart of the formula that we used in terms of u instead of x. Now, there's another retrospective that is worth keeping in mind. When we integrate or anti-differentiate a quotient, be alert to the possibility that the denominator and the numerator form an approximate function derivative pair. Specifically, look for the case where the denominator is the function and the derivative is look for the case where the denominator is the function and the numerator is the derivative of the function, or a constant multiple of the derivative of the denominator. So denominator function, numerator derivative. Look for cases where the numerator is essentially the derivative of the denominator. Here's a good one. Compute the antiderivative of tangent of x. You know, we have yet to encounter a function whose derivative is the tangent of x. So I guess the best thing to do is just to rewrite this in terms of things we know more about. So here we have the antiderivative of sine of x over cosine of x. And we're looking for a function derivative pair or an approximate function derivative pair. And without a tiebreaker, this could go either way. Cosine is the derivative of sine, and negative sine is the derivative of cosine. So cosine is exactly the derivative of sine, and sine is a constant multiple of cosine. So which one do we call u? Which one do we call the function, and which one do we call the derivative? Well, remember our retrospective. We're going to be on the alert for situations where we have the integral or antiderivative of a quotient in which the numerator and denominator form an approximate function derivative pair, with the denominator being the function and the numerator being the derivative. That's the way it works. So I'm going to write this as 1 over cosine of x times sine of x and we determine if u sub is appropriate. And do we have composite function? And remember, 1 over a function is a composite function. So the answer is yes. 1 over cosine of x, which is the same as cosine of x to the negative 1. So this is the inner function. Cosine of x is the inner function. And our rule of thumb is that we let u equal the inner function. So u equals cosine of x. Now the second thing that we look for is a function derivative pair or an approximate function derivative pair. And do we have one? We do. We have function derivative and function derivative. The way things work out, if the first part is 1 over the function, then it's going to turn out that this is going to be the function that's going to be the derivative. But let's do it both ways, just so that we can see where the tiebreaker comes in. We'll say, yes, we have an approximate function derivative pair. And let me give myself some wiggle room here. Yes. And we'll say cosine of x, sine of x, and here's our function. Here's our derivative. And our rule of thumb is that we let u equal the function. And that tells us that u equals cosine of x. Now, let's just take a look at how we could have done this a different way. We could say sine of x is our function, and cosine of x is our derivative. So here's our function. Here's our derivative. And u equals the function. which means u equals sine of x. Now we go to Criterion C. Do criteria A and B suggest the same choice of u? Well, criterion A says that u should be cosine of x, and we want criterion B to say the same thing. And with our first choice is cosine of x being the function and sine of x being the derivative, u is cosine of x. So this is how we want things to work. If we say that sine is the function and cosine is the derivative, then we're recommending that u equals sine of x, but that doesn't match our choice up here in part A. So, no good here. If we go this route, then in part C we can't say that criteria A and B suggest the same choice of u. But if we let this be our function, u is cosine of x, and criterion A and criterion B suggest the same choice of u. So now with a clear conscience we can say, yes, criterion A and criterion B suggest the same choice of u, and that means let the good times roll. Use U-Substitution. So let me rewrite what I have now. Here's what we're integrating. 1 over cosine of x, sine of x dx. And step 2, compute du. U is equal to cosine of x, du dx is equal to negative sine of x. So that means du equals negative sine of x dx. And since we only have an approximate function derivative pair, I'll leave a line blank here. Do you remember what step 3 is? Analyze in terms of u and du. That's right. Well, u is cosine of x. So this has to be 1 over u. And sine of x, whoa. I beg your pardon, sine of x dx here. Sine of x dx, I don't see that anywhere, but I see something like it. I see negative sine of x dx right here. Now, what would we have to do to both sides of this equation to make the right-hand side look like this, sine of x dx? And the answer, I guess, is either multiply or divide both sides by negative 1. And we find out that sine of x dx is negative du. So our integral is 1 over u negative du. And what this really is negative 1 times du. So what do we do with a constant factor in the integrand? You got it. We take that constant factor and move it out in front of the integral sign. Now, step 4, integrate. And we do it in terms of u. So we have negative the integral, 1 over u du. And one of our retrospectives from the last problem was antiderivative of 1 over u du is natural log absolute value of u plus c. And we have this constant multiplier outside, so that's what we get. Onward to step 5, we re-express in terms of the original variable. So what did we start out with? We started out with tangent of x, didn't we? Tangent x equals, and in terms of u, this is our answer. Negative natural log of u plus c. Now we need to express that in terms of x. So we go back to step 2. And step 2 tells us that u and cosine of x are the same. So in terms of x, this answer is negative natural log cosine of x plus c. And this is the form of the integral of tangent of x dx that our book uses. Oddly enough, our text is the only text that's ever been written that has this as the integral of tangent of x. This is correct, but it's not the common form. So permit me to write the form that other texts have. This is negative 1 times natural log of cosine of x. And let me ask you something. Natural log of x to the n is the same as n natural log of x. We can take this exponent and move it outside as a constant multiplier. Well, you know what? This is an equation. And all equations are two-way streets, which means that not only can we read the equation from left to right, we can read the equation from right to left. A constant times natural log of x is the natural log of x to that power. Well, right here, we have a constant, negative 1, times cosine of x. We can rewrite it as the natural log of cosine of x to that power. In other words, we're taking the exponent, we're moving it back up here. Now, what is something raised to the negative 1 power? It's 1 over that thing, right? So this is the same as natural log of 1 over cosine of x, oh, plus c, by the way. What's 1 over cosine of x? Secant, right? This is the form of the integral of tangent x that most texts use. We will include both forms, natural log of secant x and negative natural log of cosine x. Now that completes our exercise. Antiderivative of tangent x is negative natural logarithm of cosine of x plus c, which is the same as natural logarithm of secant x plus c. So we just computed the antiderivative of a function whose antiderivative we did not know until just now. And this is the antiderivative of one of the elementary trig functions. So let me just write down the antiderivatives of the elementary trig functions that we haven't already covered. Okay, the antiderivatives of the other trig functions. We just found out that the antiderivative of tangent x is negative natural log of cosine of x plus c, which is same as natural log of secant x plus c, absolute value. Antiderivative of cotangent x is natural log of absolute value of sine x plus c. And by the way, this is found pretty much the same way that we computed the antiderivative of tangent x. We just break this down and write it as cosine of x over sine of x and do U-Substitution. Antiderivative of secant x is natural logarithm of absolute value secant of x plus tangent x plus c. And you know what? Our book actually does have another rogue formula. It's correct, but this is the only text in the world that has it this way. Antiderivative of cosecant x is negative natural log of cosecant x plus cotangent x plus c. Every other text in the world has this. Positive natural log of x of positive natural log of cosecant x minus cotangent x plus c. We should be aware that both of these forms exist and both of these forms exist. We should know at least one, if not both, of the forms for tangent and cosecant. Having said that, for those of you who are not going on to Cal 2, and even for those of you who are, it's final exam time. Don't worry about these formulas now. They won't be on the final. And that means that if you're not taking Cal 2, I guess you don't really have to know those. If you are taking Cal 2, make sure you learn these before taking Cal 2. Learn these before taking Cal 2, or at the very latest, the first few days of the semester, commit these to memory, along with the other integral and derivative formulas. Everybody, it's been a pleasure having you as students. My only regret really is that we did this online and I never got a chance to see any of you face to face. But you never know what the future holds. And it just may be that in another class or in some other situation, we will see each other face to face. And I would be absolutely delighted to make your acquaintances, each and every one of you. And I say that with a big smile on my face, but I say it also in utmost sincerity. If I ever have the opportunity to meet you people in person, it will make my day plus. I will be delighted to meet you. And if we don't meet face to face, that's something that is sad to think about, but we might not meet face to face. But I've enjoyed having you as students and being your instructor, and I hope that things go very well for you in the future.